So I would like to talk about adaptive optimizers. So till now we have like a constant learning rate, which can pose a much greater difficulty. So what are the problems with the normal this vanilla gradient descent, the normal vanilla gradient descent that we use? So it takes a uniform learning rate and it becomes a very big and very difficult decision. As if you would take a slow learning rate, it would converge very slowly. It can take much time, but it would be stable. If you take a large learning rate, it would be unstable, but it would converge fast. So it becomes a typically hard decision to take. So the solution is to make the learning rate also a like changeable parameter. Like we are now changing the hyperparameters. So adaptive optimization calculates a unique learning rate for each parameter, as each parameter can have different curvatures. So we would calculate each parameter differently. Okay. So our first algorithm is adaptive gradient algorithm. It was one of the first optimizers, like it was the beginning in this field. What it does is it maintains a cumulative sum of past gradient descents, and there comes this formula. So I would try to explain this formula. Here, what we are doing is we have maintained a constant where this capital G is the sum of past gradient descents, and this epsilon is a constant, and this mu is a learning rate, which we usually take as eta. So what it does is it subtracts its the GT is the 1 minute. Small g is the like the gradient descent calculated at the particular time step t, and this capital G is the sum of past gradient descents. So we are multiplying this by this whole constant thing, like the mu upon under root capital G plus epsilon. So we are also changing the learning rate. This is how we are changing the learning rate. Now talking about root mean square propagation. So why root mean square propagation was created? So it addresses Adagrad's aggressive decay by replacing the cumulative sum with exponential moving average. Like in the Adagrad, all the gradient descents, like we are at time step t, we are at time step 1000. The gradient descent at time step 1 was given the same importance, which is which is generally a wrong thing. So what it does is it gives more importance to the gradients which are closer to the time step. Like if we are at 1000 time step, the 9991 will be given more importance rather than 501, or the first one will be given very less importance. So it has also this formula where we use another constant beta, and it updates the learning rate in the same way as the Adagrad. Here just the thing is the importance is given on temporal basis. Like the closer ones are given more importance, their coefficients are higher. Now moving to adaptive movement estimation, that is ADAM. Now it is now the most commonly used adaptive optimizer. If we don't know the specification of a particular neural network or our particular needs, we just take ADAM, as it is very robust. It can adapt in many conditions. So what it does is it combines the features of two things. First is the momentum, and second is the RMSProp. So what is momentum? Momentum is decaying average of past gradients, and here we call it as velocity, and it has the same formula like the previous one. And the second one is the sum of past gradient descents, which is calculated the same as in the RMSProp, and it has also the bias correction. Now talking about how we can choose our optimizer. So if you have infrequent features like natural language processing, where there is no fixed frequency, there is no fixed pattern, so choosing normal vanilla gradient descent could pose a problem, as different parameters could have different curvatures, and if we use the same learning rate for all the parameters, it could pose a problem. So here we can use Adagrad. Now when RMSProp is used, as I discussed, it has temporal dependency. It gives importance temporally based on time. So it is very good for time series data problems. Here, as the same thing, the recent gradients are given more importance than the historical ones. Now, ADAM, it is the most robust and most used one right now. It is fastest, and it is the combination of momentum and RMSProp. So it is now used for most deep learning tasks. Thank you. This was the end.